Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the University of Helsinki in the Helsinki Institute of Physics over in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how it all evolves, how it all interacts, all of the cool stuff happening inside the universe. It's a great topic. I love being a cosmologist. I love being a scientist in general. And I love chatting to people about all of the cool stuff I get paid to research and all of the cool stuff out there in the universe, even if it's not my own research. So if you're new here, welcome. If it's your first time, please do subscribe, like, leave a comment, do all of the usual YouTube stuff. Even if it's not your first time, do all of the usual YouTube stuff. It really does help boost engagement, and I do appreciate it. So hello everyone, to everyone saying hello in the comments. It's nice to see everybody here. I see David, Ange, Scott, Paul. Some of the regulars are always coming in here. It's great to see everybody again. And I know I've been away for a while. It's been 3-4 weeks since the last stream. There's been a lot of stuff going on. I was at a conference and I was visiting family in Spain, and then I was out of the theatre. And there's just been a lot of things going on lately, which has led to me not doing streams. But I'm back today. I'll be back on next Sunday, and then I'm taking another 2-week break because then I'm traveling again for another conference. It's conference season, which means full-on traveling every month for conferences and for work. And at least I try to do it in the most sustainable way possible, but still it is a ridiculous amount of traveling. So yeah, stream today, stream next week, and then there will be at least one missing, potentially two, depending on the traveling. And then in June I'll be here. Yeah, the schedule is going to be rather intermittent. On that note, I ran a Twitter poll recently about the schedule. It's kind of undecided because I've noticed that Sundays are becoming quite harder for me to stick to because I work Monday to Friday. Saturday is usually doing stuff, and then if I'm actually going out with friends or having any social events or theatres or anything like that, I often do that on a Sunday, which clashes with the streams. I know weekdays doesn't work well for a lot of people because of work. It also doesn't work well for me. Honestly, I wouldn't have the energy to do a stream during the week. I know I used to in my PhD days. I have no idea how I managed that. I don't think I'm going to shift to a weekday. So the current plan is we're sticking with the Sunday time slot. That's 7 p.m. Central European time. So 7 p.m. Central European time, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast. If I know in advance that I'm not going to be able to make Sundays, the second choice will always be Saturday. If I can't make either Sunday or Saturday, it will be cancelled. But I'm not going to do weekday streams. It will be either usually on Sundays, and Saturday will be the backup one. Yes, I do not yet bike across Europe. That would indeed be the most sustainable way. I try to do it in the sustainable while still not spending 5 days biking across Europe. I try to catch trains and boats where I can, but unfortunately I do have to take planes sometimes. As long as I can minimize my amount of flying, I'm okay with that. For the conference I just went to in Paris, I caught the flight, not in Paris, in south of France, sorry, I caught the flight to Paris and the train down. And then I joined that together with the trip to Spain, which was a train ride, and then the plane back home. So I took 2 planes for basically two trips that I managed to combine together. For the upcoming conference I'm going to, that will be in Norway, and I'm going there entirely by boat and train. So I leave Saturday afternoon, I get to the final destination Monday morning, and the conference starts Monday lunchtime. It's going to be an intense couple of days, but it's going to be fun. And then on the way back, it will be 1 plane and a few trains. So trying to do what I can, but of course it would be better if I could get rid of planes entirely, but that's not feasible right now, given that I live in a place that is quite disconnected from the main train network in Europe, especially because there's a gauge issue with the trains in Finland, and I can't believe I just went there. Hey, David Howden, great to see you too. Always nice to see you here in the comments as well. In good weather, you can get pretty far with an electric assist bike, yeah. But I think getting from Finland to other places by an electric bike might take a while because there's kind of not convenient land bridges. That's where the boats come in, and then that adds on at least a day journey if you're catching a boat somewhere. But it is fun. I love trains, except for the fact that I have terrible motion sickness. I love train journeys. So I'm happy to do as much traveling as I can by train. It is fun. And yes, I am indeed speaking very, very quickly. I did the whole 5.5-minute intro without pausing or taking a breath. Thank you for the reminder. And David, out chasing butterflies sounds a lot more fun than being inside. I hope you found some good butterflies. I actually went out to the forest today and it was really nice. There was a lot of moss everywhere. There's a lot of flowers. There's a lot of birds and pretty trees. It's just really nice outside currently. And it's not yet reached the point where it's unbearably hot and I refuse to go outside. So it's currently very good temperature to go out and enjoy the forest and look for butterflies. And I see comments already coming in pretty quickly. So yes, breathe is good. Chasing butterflies is good. I would love to travel Europe, especially Norway, get a Setsidal cardigan sweater while you're there. So getting a cardigan sweater is not on my to-do list in Norway. But yeah, traveling Europe is great. There's a lot of train connections once you get down south of Finland, because Finland, gauge problems, Russia, all of that stuff. But once you get down, it's very nice. There's a lot of places you can travel within Europe by train. And I don't know why the US isn't catching up with the train network. I remember when I was in the US last 5 years ago, I was trying to catch trains to go places and the trains were just terrible. I will be getting a pair of wings. I mean, it would be really nice to have your own wings. Can you just imagine flying? But that would be an evolutionary problem if humans suddenly developed wings out of nowhere. I love trains. Yeah, trains are good. Hot in Finland? Yeah, well, too hot for me. Anything over like 25 degrees is too hot for me, Celsius, of course. So, yeah, it's still, I think today it was 21, 22, so it was still okay. And in the forest, you're shielded from the sun, so it's the ideal thing. Okay, lots of random chit chat and stuff. Traveling is fun. If you want to follow my travel updates, you can follow me on Mastodon. It's where I post now. So my science outreach is still on Twitter, but if anyone wants to follow me for just me, that's not science outreach, you can follow me on Mastodon. It's linked to on my Twitter profile. So you can follow me there, and anytime I'm on a train journey, I do post up. Not every time, but I frequently post train updates on Mastodon as well. I will look out for this famous cardigan sweater, the Norwegian cardigan sweater. I will add that to my list of things to just look out for now because I'm curious. Okay, there was actually I realized I missed half of my introduction. So for anyone who doesn't know the format here, this is an Ask Me Anything You Want about the universe, about space, about science, about physics in general. You can ask me anything. I will do my best to try to answer. I don't have a specific topic prepared today, so we can take the stream in any direction you all want. Depending what you ask me, we'll go in different ways. If you don't have a lot of questions, I get to ramble, as I have done for the last 8.5 minutes. So this is a place to ask anything you want, any burning questions you have about the universe, any science news you might have seen the last 3 weeks. I have to admit, I've been a bit disconnected about the science news in the last 3 weeks, but there is one story that I will briefly mention. But yeah, as always, you can ask me anything. I might not have all the answers. If I don't know, I will try to tell you. If I don't know the answer, I will tell you I don't know. If I'm unsure, maybe we can figure it out. But please do feel free to ask away, and I will do my best to answer questions. There was a question by Paul pretty early on when I was talking about conferences. And the question was, are the conferences very specific or more broad in topics? And that very much depends which conferences I go to. Like I went to one in March that was called Physics Days, and it was all of physics in Finland. So it was very, yeah, I am talking quickly. So this one was very much targeting people who do physics in Finland. So that one was very, very broad. And you had a lot of different topics. And then, of course, you go to the ones that are closest to what you're interested in or to what you work on, and you don't really listen to all the talks. That one was very broad. There are other ones that I go to that are very niche, very specific. Like I went to one last summer that was specifically about dark matter. Okay, dark matter is still a broad topic, but it was kind of in a direction where at least 80% of the talks were interesting to me. The one I went to in south of France 2 weeks ago, I think it was, at the beginning of the month. Time is weird right now. Time is wibbly wobbly these days. The one I went to in Avignon in south of France was just called like Progress in Old and New Themes in Cosmology, which means it's cosmology, but within cosmology, there's a lot of topics. So out of the 4 days of conference, 2 were extremely interesting for me. A third day was half and half. And one of the days was less interesting. At least they grouped the days by theme. And then that's when I skipped half a day of conference talks and went to explore the city because it was a packed schedule. The one I'm going to in a few weeks is extremely specific. It's a LISA cosmology working group. So people who work on cosmology with LISA, doing cosmological analysis with Lisa. We're all meeting up or everyone who can make it is meeting up in Norway to discuss ongoing projects and stuff. And that's really cool. And also extremely scary, because that means I'm presenting my work to people who have worked on this topic for many, many, many years. And I'm there like, hi, listen to me talk about stuff. So that's going to be really fun. So yeah, the question of how broad are scientific conferences depends on the conference you go to. Sometimes it's nice to go to broader ones to get a bit of an overview, but we often go to specific ones that are more aligned with our own personal interests, which also makes a lot more sense. Okay, how do we know if the speed of light is correct if it was calculated on Earth and time dilation is different here than in deep space? Very nice question, Scott. So we know that the speed of light is constant. No matter what you do, no matter how fast you're traveling, if you're in a vacuum, the speed of light is always going to be the same. Light can slow down in other medium. If you go in in water, light travels slower. If you try to shine light through lead, obviously it doesn't really travel in a good way there. But light can be slowed down in mediums, but if you're in a vacuum, light always travels at the speed of light, which is convenient. Now, of course, then there's the thing like, how do we measure this? And this is something that you can calculate. This is something that you can measure in many different ways. And it's something that we have tested countless times in countless experiments for the last 100 and something years, more than hundreds plural of years. So we're pretty sure that light is the same, but there are still people looking to see if this is true in extreme scenarios. Like, for an example, if you go very close to a black hole, would it be the same? If you go somewhere in the universe where there's not much matter in a cosmic void, would it be the same? And every single test people have done show that, yes, it does travel always at the speed of light. And this is now something that we accept as, one of the few things in physics we can count on. We question everything in physics, we revisit everything, but there's a few things that we're pretty sure of. Energy must be conserved, light travels at the speed of light. These are some postulates that you can kind of take for granted, but it is good to always revisit them. Interestingly, you can actually do an experiment at home. If you want to measure the speed of light yourself, all you need is a chocolate bar and a microwave. So you take a chocolate bar, you take your spinning plate out of the microwave so that the chocolate bar doesn't move. Obviously, you put your chocolate bar on a plate to not get your microwave messy. You put the plate in the microwave, you turn it on for a few seconds, not too long, and it's important that the chocolate bar doesn't rotate. At some point, once the chocolate starts to melt, you take it out of the microwave and you'll have two lines where the chocolate is melting. These two lines will correspond to the wavelength of the wave passing through your microwave. So you can measure the distance between these two, and then you look at the frequency at which your microwave operates, you calculate those together, you get the speed of light. Of course, someone here is going to say, but you're cheating because the numbers on the microwave are calculated assuming the speed of light, and that is very true, but it's a fun experiment to do, and you get to eat chocolate. So it's pretty cool, but yes. We are pretty sure that light always travels at the same speed of light, even though time dilation is a thing, space contraction is a thing. We're pretty sure that light travels at the speed of light. And this is where things get really weird, right? Because if you're traveling at the speed, if you're on a train and another train passes you by, you have that moment where the motion seems weird. It's like, am I moving? Are they moving? Am I moving super fast? Who is moving and where? You get that thing where your motion and the other train's motion kind of get added together. But that's not the case if you're traveling at the speed of light or whatever you do. No matter how fast you're moving, light will always, always, always move away from you at the same speed of light. And that is really, really cool. Even if you're in a spaceship traveling at half of the speed of light and you shine a light, that is still going to travel away from you at the full speed of light, which is really, really, really interesting when you think about it, and something that is bizarre, but that's special relativity, general relativity for you. And on that note, there was a very big physics question just now that I did not overlook. I was just thinking how I'm going to answer it. I still haven't figured out how I'm going to answer it. So let me just recap and make sure I didn't miss any questions in the beginning. And it's going to give me a chance to catch my breath and give everyone a chance to think of more questions. I'm just going to check the comments to make sure I haven't forgotten anything. Okay, I think we went through all of these. So there was the question here by Ben of what is the Lorentz transformation and how is it used? and I'm getting flashbacks to my undergrad courses here in special relativity and general relativity. I just saw there was a second part of the question. No, that question was fine. Okay. You have to know the frequency. Yeah, you get warm chocolate. Okay. Okay, before we go into Lorentz, which is connected to the speed of light, there's another comment here. Unless C is a dimension in itself and there's a parallel universe where C is 100 meters per second. Yes, obviously we're talking about our own universe, which is the only one where we can actually make any type of observations. Whatever happens in another universe is, beyond anything we can ever probe, if there are any other universes out there anyway. So yes, C does. The speed of light is what it is in our universe. We have no idea what it is in any other universe, if any other universe does indeed exist. You can microwave small ants without hurting them because they are shorter than the wavelength. Is that true? I've never considered that. Like, how big is your average ant? The ant is what, a couple millimeters? And how big is microwave? I guess microwaves. No, so unless your ants are microscopic, yeah, that might actually make sense. I've never thought about that. Also, in general, don't put animals in your microwave, regardless of how big or small they are. This sounds like we're going down a Schrödinger experiment kind of thing. Are the ants alive or dead? But yeah, it is 3 millimeter wavelength. So if you have something that is less than 3 millimeters, would that? Yeah, I've never considered if you could safely put ants in a microwave. That's not something I do in my day job. Just in case, please don't go about killing ants. Ants are actually a really, really, really cool animal, and they bring a lot of good to the world. And I think ants are a really cool species. So please don't just go about killing ants for no reason, unless you have a valid reason to do so. But microwaving ants is not like top of the list of things I would put in a microwave, but that is very bizarre. I've never even thought about that. That's a whole tangent you're going to take me down, and then we can start talking about the fact that ants are waging war against each other, and there's this massive ant war taking place throughout the planet constantly. Wow, yeah. You microwave rice, and the individual grains are similar size to ants. Yeah, and then what you're vibrating is the molecules of water that are within the rice. Yeah, I feel like the ants probably wouldn't be too happy about being in a microwave, but I've never thought about how you can relate the wavelengths to the size of stuff you put in a microwave. That is cool. And that is a whole tangent that I'm parking for now because, yeah, that's a fun distraction. That is a fun distraction. Your microwave should be appropriately at a wavelength of 1.1 millimeters peak of CMB. Yes, you set your microwave so it perfectly matches the CMB frequency just because, why not? If rice grains are touching the heat transfer, so you need ants that don't touch each other. So I guess you can only put in individual ants or tell the ants to socially distance. Yeah, this is a very fun tangent that you all have taken me down here now. So moving away from ants in the microwave, okay, there was the comment here about Planck's constant. I'm going to come back to that because we were going to talk about Lorentz transformations. So Lorentz transformations are basically how you go from one coordinate system to another in special relativity, which makes no sense to anyone because that's a super jargony way of explaining it. So if you have something that is moving at a constant velocity, you can change from one coordinate system to another. Right, so for an example, you have so it's a very physics and mathematical thing that you do. Basically, imagine I'm on the train and another train is passing me by, and I'm in my own coordinate system sat on the train, but then I want to measure a velocity relative to the other train and not relative to me. So what I can do is I can kind of project my coordinates, my space-time coordinates, or project myself onto the other train, like not physically astral projecting or anything like this. Just imagine if I could describe myself in that coordinate system, and then I can describe something from that point of view. This can only be the case if the train is moving by at constant velocity. If the train is accelerating, then it's going to be quite hard for me to jump into that thing because it's accelerating. So that was a very hand-wavy explanation there. A Lorentz transformation is something you do to move from one coordinate system to another. So say that I'm here with my coordinate system. I have, my origin, I'm 0, 0, 0, 0. You have up, down, left, right, in, out, and a time dimension. You have your forward your 4 dimensions, and you want to project this coordinate onto a different coordinate system that is moving at constant velocity. For small velocities, this is a pretty straightforward thing to do. But once you approach the speed of light, or even half of the speed of light, then you need to consider things like space contraction and time dilation. So how the coordinates change when you move into a system that is moving at a different velocity. Lorentz transformations are used if there's constant velocity between the two frames being, for an example, me and a rocket moving past half the speed of light. So a Lorentz transformation lets you move from one coordinate system to another, taking into account effects of special relativity. And that is a short that is a short and hand-wavy answer. I hope that is a convincing answer. If not, we can go through it a bit more carefully. But we're also not going to bring out math because I don't do equations on this show. But there's always this like gamma factor that is related to the velocities, and things get funky when the velocity approaches the speed of light. But the Lorentz transformation lets you take care of this, moving from one to the other. Oh, that tea is still hot. I haven't yet reached a time when my tea is drinkable. As people know by now, I can't drink very hot tea. Okay. Science is a hand-wavy discipline. It really is. If you met scientists, we're all like hands flapping everywhere, especially if you're from the south of Europe. Hands flap all the time. It's really fun. You know, I grew up in in Spain, in a Mediterranean country where you communicate with your hands, and my hands do not sit still. So yeah, when I say hand-wavy explanations, it's both literally my hands are waving, and also I'm using the metaphorical meaning of it's a hand-wavy, wishy-washy explanation. But yes, science is exact for some things, precise for some things, and very hand-wavy for others. You know, this whole dark energy thing is like, it's there. Don't ask too much because we're still trying to figure it out. Wouldn't that implode the universe or something? I'm missing what that was related to, but please don't implode the universe, at least not while I'm doing a stream. That would be, bad for business if you implode the universe because of something I said. That can't look good on me. I take no responsibility if you guys go out or you people go out and implode the universe. Please don't do that. Now I have to find a comment that's a response to. The ants in the video were fine, but I can't prove it wasn't fake. Yeah, I'm gonna look into this whole ant in a microwave thing because I think this whole thing is fascinating. In fact, there's a high chance I'm gonna distract everybody at work tomorrow with this. And it's just such a cool thing. But please don't put ants in microwaves unless you're sure that it's safe. Because I like ants. Ants are very cool. As long as they're not in my house, ants are very, very cool. I had all the Transformers when I was a kid. I didn't remember Lawrence. Haha. Yes, very funny. Okay, there was I'll answer these questions, then I'll go back to the previous ones. No, I am not yet doing sign language, although I do actually want to learn sign language. Someday I would like to do my stream simultaneously talking and with sign language, but I know that's really, really difficult and it would just confuse a lot of people. But I do actually want to learn sign language. I think that's something that more people should learn. But no, for now it's just me hand wavy because I don't know how to keep my hands still. I'm not good at sitting still in general. I am aware there was a question about the Planck constant or the Planck rates. I'll come back to that. Does accelerating expansion mean space in our universe is negatively curved just by definition? Okay, I thought we were going on with the accelerated frames of reference. Paul, I'm going to put a pin in that question. It is a great question. Let me come back to it. From what I can tell, consumers' microwave operate at 12.2 centimeters. That kind of makes sense because when you do the chocolate bar experiment, that's the distance in between. So, and then the way you heat things up is by the rotation. Then you get things to heat up more evenly. But I'm really curious how it would work for things in between the. Yeah, I'm gonna have to look into this. Okay, so more questions here. Someone mentioned the CMB. Haha, indeed. Someone mentioned the CMB, and it has been 25 minutes, and you still haven't got it yet. And I'm not going to do it just yet. Okay, gamma ray bursts. Okay, let's go back to the question. I'm trying to answer them in order. I notice that all the questions now are going in different directions. Speaking of fundamental constants, question from David Howden. Can you explain what Planck's constant and why it is important that it be constant? So Planck was a physicist who did a lot of stuff for science, There's a lot of things associated to him, like the Planck length, which is the smallest length we can have, or the Planck time, which is the smallest time we can conceive of. And then we have the Planck's constant, which is h, which gives you the relationship between the energy of a photon and its frequency. So based on the wavelength of a photon, so a photon is a particle of light, as every particle, it also has a wave associated with it, in this case, the electromagnetic wave. This wave has a series of mountains and valleys, as all waves do. This gives me the perfect excuse to bring out the slinky toy. So every wave in the universe has mountains and valleys. You have the wavelength, which is the distance between two mountains or two valleys. And then you have the frequency, which is how many ups and downs you're going to get in a given interval, usually in seconds. And you can relate the frequency or the wavelength of a photon to its energy, and you do this via the Planck constant. Energy is equal h times the frequency. The Planck constant relates these two, so then if you have a photon at any energy, you can calculate the frequency and vice versa. We're used to thinking about colors. Now, colors are just a specific frequency of the electromagnetic spectrum, and from there you can get a specific energy. So the reason it's constant because it's the relation that Planck found between these things. And it's also used in quantum mechanics a lot. So there's a lot of things that you can just throw in the Planck constant because it relates it's the mass energy equivalent. It relates the energy or the mass of something to its frequency. So it's something that is used. So the number is an experimentally measured number. But if it weren't constant, then everything we know about quantum mechanics would be wrong, basically. And there would be no way of relating the frequency of light to its energy. And this is something that we do all the time without thinking about it. When we look at a light bulb, we're given its energy, but what's actually coming out there is light at a specific combination of frequencies with specific wavelengths, right? So, and then you have the whole watts thing thrown in. So Planck's constant, we know the value of Planck's constant by experimental testing. And it's constant because otherwise nothing that we think works would work. So we're pretty sure it has to be constant. Again, this is something that you can test in a lot of different circumstances in a lot of different ways. And it does seem to be very, very constant. Hope that answers your question. If not, we can also revisit this. And if anyone thought that sounded like I was stalling and reading a definition, that is because that's exactly what happened. I just quickly Googled it to make sure I was answering the thing correctly. So if you ever see me stalling and then typing, it's because I'm bringing up an aid, because sometimes my brain doesn't remember everything, and I wanted to make sure that I answered the relationship correctly there. 28 minutes into the stream, so 35 minutes after I made my tea, it is now drinkable. Okay, back to more questions. We were talking about imploding the universe. Please don't implode the universe. Let me just see if there were replies to what I was saying. Let's go to the H bar. Yes. So scientists can't say half of a Planck time. No, a Planck time is the smallest time we can think of. Half of a Planck time wouldn't make sense. At some point, you reach an indivisible unit, and that indivisible unit is either Planck time or Planck length. Having a fraction of a Planck length doesn't make sense by construction. So yeah, we always get either a slinky or a CMB or both. Yes, you can give me an A or B question. The answer is always going to be both. Presumably why photographers measure white balance in Kelvin. I didn't know that they did, but that does make sense, actually. Yeah, so that's a cool fun fact of the day, that you can, because of, quantum physics, Planck constant, you measure stuff like that. Okay, so back to the question, and the comment here that David Dunn made about H bar is because often if you're doing quantum physics, instead of using the Planck's constant, which is h, you prefer to use the reduced Planck constant, which is h divided by 2 pi. And because h divided by 2 pi is cumbersome notation, we do an h and we put a bar through it. Like, if you like it, you should have put a ring on it. If you like it, you put a bar on it. In the case of Planck's constant, that did not go as well as I thought it would go. That sounded so much better in my mind. Anyway, Planck's constant is Planck's constant. H bar is Planck's constant divided by 2 pi, and then you can make fun jokes like let's go to the H bar. And there is actually an online conference that I've been to several years in a row now that has different rooms, and the chill room where you go for coffee breaks is called the H bar, because haha, we're very funny. Physicists are very funny sometimes, usually, because we're weird. Okay. Question about the accelerated expansion of the universe. I love this question. I mentioned dark energy. Someone asked accelerated expansion. Great segue. I'm not sure which came first there, but let's go with it. Okay. Question by Paul here. Does accelerating expansion mean space in our universe is negatively curved just by definition? Why do we say it's flat? Love this question. So there's two parts to this question here. And first, I'm going to talk about the flatness, and then we are going to go back to the accelerated expansion of the universe. So we know that our universe is homogeneous and isotropic. This means that our universe looks the same in every direction from wherever we look. Obviously, this is not true on small scales. Doesn't that also give us Planck heat as the hottest temperature possible? No. We just use it for Planck sign, Planck length, Planck mass. Everything else, Planck is not indivisible, just those three. Okay, so the universe looks the same in every direction from wherever you look. Now, of course, this is arguably not true. If I look at the moon, it's very different to looking at the sun, for an example. But what we mean when we say the universe looks the same in every direction is on large enough scales. If you take a step back and you look at the way galaxies come together, whichever patch of the universe you look at, it's going to look the same. There's no privilege point. It doesn't look special to us. Wherever you go in the universe should look the same in any direction. Once you've got a universe that is homogeneous and isotropic, there are three possible curvatures you can have. You could have a flat curvature, which means, flat. We're used to flat. You can have a spherical curvature, or a negatively curved thing, which would be closed. Or you could, positive would be closed, depending what you're talking about here. You can have a closed spherical universe, or you can have an open hyperbolic universe that kind of looks like a Pringle crisp or a horse saddle, depending where your allegiances lie. Are you a Pringles person or a horse person? That the world is divided into those two. I'm sure this is not true, but we have enough other binaries that are not true that people believe in. So horse versus Pringles, that's it. Are you a horse person or are you a Pringle person? Anyway, tangent. So there are three possible configurations. A universe could be flat, it could be a sphere, or it could be a saddle or a Pringle. And you might all be thinking, what does it mean that the universe is flat? This is bizarre. We know the Earth is not flat, the Earth is a sphere. But when we talk about curvature in terms of the universe, what we basically mean is if you draw a triangle somewhere in the universe and you add up the angles, if the universe is flat, these add up to 180 degrees. Yes, the two genders, horse saddle or Pringle. Thank you. I'm so glad that somebody got where I was going with that. Thank you for that. I wondered if anyone was going to pick up on that, so thank you. Yes. I love how many tangents we've just gone down today. Okay, scattered brain today. So, coming back to the shape of the universe, we know that the universe is flat. And how do we know this? This is the question that was asked. And one of the biggest pieces of evidence we have for a flat universe is, you guessed it, the CMB, the cosmic microwave background radiation, 34.5 minutes today. The CMB is the oldest light you can see in the universe. It is the background in whichever direction you look. This is the afterglow of the Big Bang itself. Saddles came first, but Pringles taste better. Yes. How big would the triangle need to be to notice the differences in angles? That is a great question. It would depend on how curved the universe is. So if you have a small curvature radius, then just drawing one triangle would be enough. If it's really, really, really big curvature, you'd have to draw a really, really big triangle to see the difference. Mathematically, it's about how our equations work, but we use triangles because it's easier to think about. So this thing that you can see up here, CMB, cosmic microwave background radiation, this is the afterglow of the Big Bang itself. And this gives us a huge amount of information about the early universe. And one of the things that we can notice from this, or that we can learn from this, is that the universe seems to be flat. There are no hints of any curvature within the cosmic microwave background radiation. So our evidence seems to point to the universe being flat. But there was a second part to Paul's question, which was in fact the first part, and I just reverted the order, which was about the accelerated expansion of the universe. So we know that the universe is expanding, and this expansion is getting faster than it was before. So the universe is expanding, this expansion is speeding up. It is getting faster. We're in a phase of accelerated expansion. And let me go back to the phrasing of the question. Does accelerating expansion mean space in our universe is negatively curved? So that was one possible explanation. Like, how do you account for everything expanding? Does this mean there's some type of curvature? However, we don't think that's the case. There appears to be some type of energy driving the accelerated expansion of the universe. How do we know that? Again, cosmic microwave background radiation. From the CMB, we know that we need about 70% of the energy budget of the universe to be in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe. Okay, so what happens if we take out dark energy and add in more curvature? Does this solve, what happens? What happens is the CMB would look different. You can do this experiment. You can play this game. So usually when we do CMB analysis, we use lambda CDM. Lambda stands for dark energy, CDM stands for cold dark matter. This is our best description we have of the cosmos. It's the best description we have to explain everything we've seen out there. And this only has 6 parameters. You only need 6 numbers to explain the CMB, which is pretty cool. These are 2 numbers that gives you the starting condition. So what happened after inflation and in the early universe. Then you have the age of the time at which stars turned on. Then you have the amount of dark matter, the amount of normal matter, and the amount of dark energy. You put these 6 parameters in, and then you get the CMB. And what some people have done is say, okay, what if I add curvature as well? What happens? Does dark energy disappear if I add curvature? And it doesn't. You can't explain the CMB with only curvature effects. You need something else like dark energy. And this is even more apparent when you look at things like supernova, which are exploding stars. Now, exploding stars, supernova, are bright, huge things that you can see, hopefully, if you're lucky. When a star reaches the end of its lifetime, it collapses and it explodes. And this produces a huge burst of light and energy. And you can use this to get an idea of how far away things are. Kind of like if you hold up a light bulb and I tell you this is emitting 100 watts. As you get further and further away, you're going to receive less light. So at some point, you can calculate how much light you're getting from the light bulb, and based on how much it's emitting, you can calculate your distance. We can do the same with supernova. We know how much energy they're emitting, so we can backtrack and see how far away that supernova is. So you can play the game backwards. So supernova have shown us that we can find supernova in nearby galaxies. Using these, we've been able to see that these galaxies are moving away from every other galaxy gradually faster and faster. And this is what we consider one of the biggest pieces of indirect evidence for dark energy. And you can't explain this only with curvature. Some people have tried to get rid of dark energy by putting in curvature, but you can't fully explain everything. Now, then there's the question of, could you have a mix of dark energy and curvature? And people have tried that. But again, the CMB is basically like, sorry, no. We like a universe with no curvature. Then there's other things, like if you cut the CMB data up into chunks, there are hints of curvature, which is very fun. But it's not just the CMB. There's also things like the average distance between galaxies. And this also points towards there being practically no curvature, or if there is any curvature, right? If there is any curvature, it has to be really, 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 really small amount of curvature, which means that then you'd need to draw a very, very, very big triangle in order to see any type of curvature there. But if your curvature has an effect that is smaller than a Planck length, you would never be able to measure it. And I'm just amused at the comments here. Scientists should put a bounty on dark matter, and the response of that's called the Nobel Prize. Yeah, basically. So on the topic of supernova, because excellent segue here. There has bit of science news. There is currently a supernova visible in close close by, 6 megaparsecs away, which is not huge, but also it's close enough that we can see this. So I think it was Friday evening, the notification went out to a lot of astronomers like, hey, look up there. And there is indeed a supernova currently. It's not yet visible by the naked eye. They're not sure if it's going to be, but there is a supernova going off right now. I mean, obviously not right now. It went off billions of years ago, but the light from the supernova is reaching us now. And this is the type of event that only happens once every 40 to 50 years, every couple of decades. So when it happens, it's really exciting because we get to observe the full supernova lifetime, the explosion and everything. It's 6 megaparsec away, which is a bit far, but also close enough that if you have a decent telescope, you can already find it in the night sky. And this is pretty cool. I have just seen it because I logged onto Twitter on Friday. Bad mistake logging onto Twitter. And basically all the astronomers I know were like, "Ooh, supernova!" And it's not Betelgeuse yet. But it would be cool if Betelgeuse goes supernova sometime. Betelgeuse is a star that keeps going like, I'm going to go supernova. No, quote you, no. So Betelgeuse is a star that we know is going to go supernova at some point, and it will be really cool when it happens. It's probably already happened. We just haven't received light from it yet. But yeah, there is currently a supernova event happening, and this is really cool. So I don't have more information to give you on that other than people are excited about this. Scientists excited, that's always cool. So if you have a telescope and you know where to look, which you can find online, 6 megaparsecs is 19.6 million light years. Thank you for that calculation, Paul. I could not do that in my head, did not want to. I know it's like a factor 3, 4 more or less, like 3 point something. So about 20 million light years away, which means that this supernova explosion happened 20 million years ago, and we're just seeing the light from it now. But that's not too far. We're seeing something that happened 20 million years ago, yeah, but it's kind of small on astronomical distances. You're getting notifications from LIGO again. Yes, that is another cool thing that is happening. I am aware that there are questions I haven't answered yet. LIGO, one of the gravitational wave interferometers that we have, the Laser Interferometer Gravitational Wave Observatory, that's the name that was somewhere in my brain. Yes, LIGO is one of the ground-based detectors of gravitational waves. They're doing an amazing job together with Virgo. And they've been offline for upgrades. They've been upgraded like Cybermen over the last couple of years. And now they've turned on again, which means with increased sensitivity. So we've already had 3 full observing runs of LIGO and Virgo. And now we're going to get observing run 4. It's starting on schedule. And already in the training, like the engineering runs where they're just seeing what's happening, they've already started picking stuff up. So it looks like the upgrade worked. It's going to be even more sensitive than before. And yeah, this is really, really cool, right? The fact that we can use lasers to measure gravitational waves is something that will never fail to amaze me. It's something that 100 years ago, 100 and few years ago, Einstein said, we'll never measure this, we will never have the technology. And now not only are we measuring it, it's become so commonplace that you can subscribe to notifications and you can get a push notification like, hey, we found another gravitational wave event. Hey, we got another one. And we've gone from this is a technological impossibility to, oh, look, I got a push notification. There's another gravitational wave. So yeah, that is so cool. And yeah, LIGO observing run 4 is starting basically now. There's going to be so many cool things coming out of that. Okay, so there were some questions I missed. Let's go back to some questions. Is it possible is it possible that just the part of the universe we see has zero curvature but non-zero curvature in other parts? So if there were differences in curvature in different parts of the universe, it would be quite hard for it to look as homogeneous and isotropic as it does. Now, of course, you can have bits of local curvature, very, very local. For an example, if you have a black hole, you're going to curve space-time, so there you do have curvature. If you look at a cluster of galaxies, you're going to have a bit more curvature than in a cosmic void where there's no matter, because we know that space is curved by matter. Space-time tells objects how to move, objects tell space-time how to curve. So the more gravitational objects you have, the more space-time is going to curve. So you do have local curvature in that regard. But when we talk about the curvature of the universe, let's take a step back and look on average how curved is the universe. And then if you have a patch where you have a lot of curvature, you need an explanation for that. Usually it's like there's a galaxy or a bunch of galaxies or dark matter or something. But when you look at the average curvature, it all kind of averages out to zero curvature everywhere, according to the CMB. But there is still a bit of room for tiny, tiny bits of curvature. And it could just be that the curvature is so small that we haven't been able to see it within our observable universe. And at that point, if we can't see it, does it really have any effect if it's not in any way noticeable within the observable universe? Okay, back to questions. I know there were a few that I overlooked. Okay, I scrolled back a bit too far there. I'm back into the ants and microwave comments. I love that I have infinite scrolling here. It makes things so much easier. Not me throwing shade at previous streaming applications I've used. Okay, could you talk about how gamma ray bursts are used to study the early universe? Gamma ray bursts are amazing. There are some things in the universe that produce a huge amount of gamma ray bursts. Like gamma rays is the high end of the electromagnetic spectrum, very high energy. It's not going to turn you into the Incredible Hulk, at least to the best of our knowledge. But gamma ray bursts are just bursts of, as the name implies, bursts of gamma rays that you can see in the universe. And there's some question as to what is causing these. It might be black holes emitting stuff. It might be the center of galaxies. But gamma ray bursts can be used to study a lot of cool things. And some people are now trying to use gamma ray bursts to study early universe. And I don't know much about this. It very much depends on what produces the gamma ray burst. But measuring these gamma ray bursts will tell you about these different objects. And I did actually do a whole stream about this many months, even years ago. No, it was in the HAPS day, so I must have this somewhere. So was it a stream? Yes, I remember the stream in question now. Yes, because some people have said that you could actually use gamma ray bursts to measure the expansion rate of the universe, which is really cool. Because depending on how you measure the expansion rate of the universe, you get different answers, which is a problem because you'd hope that asking the same question different ways gives you the same answer. And it could be that if we get enough gamma ray bursts, we might actually be able to get a measurement of how quickly the universe expands. So that's pretty cool. As to what else they're doing with gamma ray bursts, I'm afraid I don't know. I don't work enough on gamma ray bursts or at all on gamma ray bursts. So that's just a brief answer. There was a question, where do you subscribe to these notifications? There's an app for it. As always, there's an app for everything. You can get I think it's the official LIGO app and has push notifications. Just realized that LIGO is an acronym and the first word laser is another acronym. Yeah, that's physicists for you. That's how we do acronyms. Never ever ask a physicist to do an acronym for you, because we will take random letters from random words to make a new word. You know, I say that as if I don't do it. I submitted a Marie Curie grant application some months ago. There you always have to come up with a project acronym. And my project was called, what was my project called again? So my project's name was phase transitions from, no, sorry, my project name was something like phase transitions from gravitational waves to LISA and back, or something like that, like something long and wordy. And my acronym was phonic. I was like taking the O from gravitational waves, like, oh, there's an O there, and the N from the middle of the word. And yeah, there's actually a web page that lets you generate acronyms a la physicist, and you put in your like 8 words and it will pull out random letters like, hey, you can spell out panic, call your project panic. I didn't call my project panic, but I could have done. So yeah, never ever ask a physicist to make an acronym, because it is, we do not know how to do acronyms properly. Okay, we just went, there's an annoying fly here. Apart from my usual hand wavy, I am actually chasing away an annoying fly. Maybe the fly should go in the microwave. No, we do not put animals in microwaves regardless of their size or how annoying they are. I feel like this is, YouTube sometimes adds automatic chapters to my streams, because I don't go back and add chapters, so YouTube does it automatically. And it just picks out random phrases that I say. and uses them as chapter titles. I was looking through an old stream and it had a chapter called Cucumber Tea is a Singularity. And I was like, did I actually say that? And I clicked on it and yeah, I did. So I'm now worried that this video is going to have a whole chapter called Don't Put Animals in the Microwave Unless They're Small Enough or something like that. So just in general, if you see YouTube chapters on my videos, know that it's nothing to do with me and it's auto-generated and I don't necessarily agree with the chapter splitting that it does. Okay, catching up with the comments, you either get Slinky or CMB. You did indeed get both today, but you have not had enough CMB today, I think. Okay, question here about black holes. Is it possible to have a black hole that does not emit Hawking radiation? I love this question. So Hawking radiation is a hypothetical thing that black holes... Chapter 7, Deanna chased a fly. Yes. You're often putting insects in the fridge. I mean, I think they do well in the fridge, right? Aren't you supposed to? Because then it kind of stuns them and then you can get them out. I remember Isa from the Bug Scope telling us about having animals in the fridge because it was good for you. Yes, anyway. Yes, don't put a fly in a microwave. It will end badly. Laser is also a word at this point. Yes, okay. Black holes, Hawking radiation, that's where I was. I was just like, wait, where was I? Okay. So Hawking radiation is this idea that you can produce particles in the universe. This is something we know. Sometimes you can kind of borrow energy from the universe. You produce a particle and an antiparticle. These are called virtual particles, and they immediately annihilate and give back the energy they borrowed. This is happening constantly in the vacuum of space. Particles spring into existence and immediately disappear. Fine. But if this happens close to the event horizon of a black hole, you can have the fun situation where one of these particles, the particle and antiparticle, are created, and one of them falls into the black hole and the other escapes because they're created right on the event horizon and they go in opposite directions. If this happens, you can't give back the energy that you've borrowed from the universe. So what happens is, to compensate this, because energy must be conserved, then the black hole slightly loses mass to compensate for the particle that was escaping. Now, this particle did not escape from the black hole because nothing can escape from a black hole, but it's pair produced on the event horizon. One goes in, one goes out. The black hole loses mass. This is known as Hawking evaporation or Hawking radiation. And eventually these black holes could actually evaporate completely and dissipate, would be a better word than evaporate because it's not a liquid. So a black hole could actually completely dissipate through this process. And then there's the fun question of what on earth happens to the energy contained in the black hole? We're not sure about that one. But the thing about Hawking radiation is we've never been able to observe it. It's something that theoretically should exist. We think it does, but it's not actually something we've been able to observe. So the question was, can you have black holes without Hawking evaporation? Now, technically, all black holes will have this process. Then you have things, even if you have a spinning black hole, the math gets a bit more complicated, but you can and still should have Hawking evaporation. But then the actual question is, do any of these actually have this? And there we're less sure because we've never actually measured this. So it's something that can theoretically happen. It should happen. We think it does, but we're not actually sure. So yeah, we think that Hawking evaporation is a thing, but we've never seen this. So we're pretty sure it should be there, but we've never really seen it. So yeah, there's that. Then if we find black holes that don't have it, that could probably mean that no black hole has it, maybe. But there could also just be some where this doesn't happen for random reasons. But in general, we think it should be the case with black holes. We just haven't seen it yet because it's quite a difficult thing to actually kind of measure. Black holes are difficult to study. We can't see them, which makes everything harder. You just notice their effects. So putting insects in fridge slows them down for photography examination. It's also how magicians do the resurrect a dead fly trick. I did not know that. I've actually never questioned how magicians do their trick. It spoils the fun for me. I used to try to figure it out, like how are magicians doing this? There's an answer I need to know. And I'm just like, they've tricked my brain. That's okay. I could probably figure it out. I'm sure there's a YouTube video explaining the trick, but that defeats the point. I like to be wowed and impressed and then like, I guess there's a solution. I don't believe that magic is real. So there must be a solution. Someone's probably figured it out. I don't feel the need to learn that, but that makes sense that they resurrect a dead fly by freezing it. And then as it warms up, it's like, I brought it back to life. It feels more like trickery than magic, but that's all magic for you, I guess. Okay, going back, because I think there are still some questions. There are probably still some more questions I missed. Black holes, we've just done that one. Planck heat, we did that one. Horse saddles and Pringles, yes. Okay, I think we might actually have gone through all the questions by now. Is that the case? Let me just see. Betelgeuse, yes, and then we talked about supernova and the one that is going boom right now, or not going boom right now, but that we're seeing right now. And I think we are indeed all caught up to it. The questions now. Okay. To the ant crowd, if individual ants were safe in the microwave, let's assume, but then a bunch of ants all connected to each other, would they all of a sudden no longer be safe? Yeah, I'm not even going to get into what happens if you kill an ant that is special for the colony because you put it in a microwave. What happens to the rest of the colony? Let's not go there. But yeah, you saw on social media that if you heat empty space high enough, you can create a universe. Heat. If you heat empty space high enough, you can create a universe. Is that string theory? Mm-hmm. I wouldn't call that string theory. I would call that a social media misleading description. I'm not sure really what you can do in that regard, because if you put enough energy in something, that energy must be conserved. It's going to go somewhere. You put enough energy into something, you can create particles, you can do stuff. This is what happened in the early universe. And heat is a type of, yeah, I'm not sure if you can just heat something up and a boom, universe appears. That doesn't sound like something that the usual way of creating universes. Of course, I say that as if I know how to build a universe. Like, here's how you build a universe from scratch. Of course, we don't know how to do this. So what we do is we take this thing in the very early universe and we move forward with it. Where this thing came from, what came before this thing in the early universe, that's something we can't really answer. But yeah, if you put energy into something, something's going to come out because energy must be conserved. You should do a satirical video, why I haven't found dark matter and how I plan to do better. Yeah, the amount of times I start this stream and someone asks me, like, so have you found dark matter? It's like, well, no, sorry, I haven't found dark matter yet, actually. I'm working on it. Leave me alone. So yeah, a lot of people expect that I'm going to find dark matter, but I don't even work on dark matter anymore. I work on gravitational waves, which is a very cool topic. And someday maybe I will join these together and do dark matter with gravitational waves, because that sounds amazing. And I'm not the only one thinking about this. But yeah, there's so many ways you can put these two together. It's cool. Dark matter is cool, literally. Gravitational waves are interesting and amazing and wavy and wibbly wobbly. The CMB is still the CMB and still something I hold dear, but gravitational waves are currently my research topic, and I'm super excited about the stuff we're doing with this. There's a whole TV show that reveals magic tricks with good production value and all. Hasn't it called Penn and Teller or something? I know Penn and Teller are magicians. I think there was a show where Penn and Teller were explaining magic tricks. I'm not sure. But there's also a lot of YouTube videos where there's like, here's how they do this trick. I'm like, okay, cool. Okay, I think I got through all the questions, and it's almost 1 hour since I started the stream, so it is almost time to wrap up and pack up for the day. And hands are still waving constantly as they do. So yeah, I know it's been a couple of weeks that I haven't been online. As mentioned, there's a lot of stuff going on, conferences, travel, theatre, stuff in general. I'm doing a stream today. There will be a stream next Sunday. There should be, unless something random happens. And then there will be a break again because traveling again on a train, unless I do a stream from a train. I could do a stream from a night train. Oh wow, that would be so chaotic. Not gonna happen. But that would that would be very funny, like a very sleep deprived me getting motion sickness on a train, trying to tell you all about physics. That is a recipe for disaster. That is absolutely not going to happen. But I just realized in 2 weeks I will actually be on a night train at the time when I should be doing a stream. So there's that, but it's not going to happen. Speaking of string theory, incoming nerd snipe, remember supersymmetry? Yes. So I know I have mentioned at some point that I want to do a whole stream about supersymmetry because people keep asking, or about string theory. There are some people in the office who I've mentioned this to and who might actually be up for doing a stream about string theory or about supersymmetry. We'll see. You tried live streaming from a train, connection issues made it impractical. Yeah, I imagine there will be connection issues. Also, Restream, which is what I use these days, doesn't work so well on phones as far as I know. So Night Train is two very cool songs, one old jazz and the one by Guns N' Roses. My favorite song about Night Train is actually City to City. But there are many, many, many good songs about night trains and about trains in general. You know, trains are a really cool thing and people write a lot of songs about it. And you can never you can never ever beat Midnight Train to Georgia as far as I'm concerned. That is an amazing song. Spanish Train is also very, very good, a bit too much talking for my liking, but very, very good. But Midnight Train to Georgia is just, you know, a fun song in general. Okay, so I think we're all done with comments. I am getting a bit tired of talking, as you can all notice by the coughing now. But that will pass. So, you've never heard the Spanish Train, Scott? You have to look it up. It's a great song. Christopher, I believe the name is. Not sure how it's pronounced. Great song. Yes, go listen to it. Okay, so trains were invented about a mile from my current home. That is a very cool fact, David. That is like so cool. Do you use that as an icebreaker? Like, hi, I come from the place where trains were invented, because I would absolutely use that as an icebreaker. I feel like you have to know a lot about trains just because of that. So that is a very cool fact, actually. I mean, I don't even know where trains were invented, but I know someone who would know that, and that's a very cool fact, cool party fact. Like, hey, I live and trains were invented right there. Haha. Very cool. Okay. We've had a lot of really fun tangents today with ants and with saddles and Pringles and microwave stuff has happened in this stream. It's always entertaining. You know, every time I spend a couple of weeks without doing the streams, getting back into it requires that bit more inertia, and I'm always like, okay. And then I get back into it and it's super fun and we do a lot of random topics and I really enjoy it. So thank you everyone for all of the cool questions and comments and tangents we've gone down. It's been really, really fun. Was happy to come back and chat to everybody again. I should be online again next Sunday, same time as always. If you subscribe to the YouTube channel, you will get the notifications. I have finally figured out how to change my YouTube layout so that if you go to the YouTube channel, which is YouTube/Cup of Cosmology, if you go there on the homepage, I've now actually changed it. So instead of showing you the uploaded videos, it does show you the streams. And right at the top, it shows you the next upcoming stream if I've already scheduled it. So hopefully that will make it easier for everyone to know when I'm online again. I might even already schedule the one for next Sunday, because then it's there as a placeholder and then you know it's happening. Going forward, if I can't make Sundays, it will be shifted to Saturdays, but I'll always post this with advance warning. For updates on Cup of Cosmology, you can follow me on Twitter. I'm DCHooper91. For non-cosmology life updates, you can follow me over on Mastodon. I'm DCHooper at tech.lgbt. You can follow me on Mastodon as well. There's a lot of cool stuff happening on Mastodon. I can't believe I became one of those Mastodon people, but here we are. Okay, thank you everyone for joining. This has been really, really fun. We've had a lot of cool questions, cool conversations. Always great to do this. So I will be back online next Sunday, same time as today. I hope to see you all then, and I hope in the meantime you all stay safe and take care of each other.